Hello, I'm Braden Lenning, and this is my final project for MIT Robotic Manipulation. It is about optimization of rail positioning in large-scale 3D printers. So this is a rocket created by a company known as Relativity Space. It was launched back in May. What's exciting about this is that it's actually 70% 3D printed by mass. So how this is done is these large-scale metal 3D printers. You can see that there's a rotating print bed, and then there's the robotic arm that holds the welder and moves back and forth to position it properly. I wanted to simulate this, so I brought this into Drake, starting with the print bed. This is a custom SDF file. It's just a simple sinusoidal motion moving back and forth with an inverse kinematic solver or controller. So here is the mock-up of the robot on the rail. You can see it can move back and forth on the rail. Key difference here is that the third joint is actually locked. So industrial robots are typically 6 axes. The EWA is 7 axes. So by removing or by locking that third joint, it acts like an industrial robot essentially. Awesome. So here is a simulation of the robot simply tracking a point on the print bed as the print bed rotates back and forth. Alright, so now we get into weaving. So we can see here, as the print bed rotates back and forth, the robot arm moves, or rotates around the robot arm moves back and forth. The blue lines indicate, or the blue dots indicate the desired path. That's the path we want the robots to go on. And the red line is the actual path that it goes on. You can see here there's a large phase lag, but the magnitude is still pretty similar. Awesome, so here is another weaving operation. What's cool about weaving is that it actually lets you determine the thickness of your material. So here we can see robot arm moves back and forth as it prints, and this is with a rail position of 0.75 meters. And the rail position is the distance from that blue vertical line to the robot arm base. So it's like the movement along the linear rail. So this is the output. We can see the desired weave trajectory versus the simulated, which is like what actually happened trajectory. Here's with a different rail positioning, with it much closer to the bed. We can see it's a lot tighter positioning. And we can see here that it's a little bit different of an amplitude ratio. So as we can see, a ratio of simulated amplitude to desired amplitude is 0.4. And that's actually what we're comparing across different configurations or across different rail positions. So here's a graph of rail position versus the amplitude ratio, where 1 is like the perfect ratio. The red dot is actually where the Jacobian is the highest, and it makes sense that that has the best performance. So I just want to say thank you to all the great staff in robotic manipulation.